Okay, so we're for the review session. I'm starting with 2008 question number 2. And this is kind of like a general lab type question. And so here's the deal. So if you've got this MgCl2 dot something in H2O. So we talked about hydrates before. Like when we were talking about like when we all did that enthalpy of solution where you like added water to anhydrous copper sulfate and then you added water to hydrated copper sulfate. Okay, so hydrated just means that it doesn't mean that it's aqueous. Okay, and everybody says, oh, it's hydrated, it's aqueous. No, all it means is that at an atomic level you have MgCl2 and then there's some fixed ratio of water molecules. Grab those 2 sheets. So there's some, we're doing this 2008 question number 2. So there's some fixed ratio of water molecules to and typically it's like an ionic compound, in this case like magnesium chloride. Like if you've ever seen Epsom salts, okay, which is magnesium sulfate .7H2O, hydrated copper sulfate is like CuSO4.5H2O, okay? So it's just water molecules that are attached to it. It still looks granular, so you can't really look at it and go, oh, it is like we can put it up to a microscope and go, oh, here, let's count the water molecules around it like we can like petals around or in the center of a flower. So now think of this as a bigger picture, right? So you got this empty container like this, typically like a crucible, okay? And you're going to add that to that. Now, think this through. Why did you have to add heat to it? From a thermodynamic standpoint, what was the purpose of adding the heat? To break bonds or to form bonds? Break bonds. You wanted to break the bonds that hold the water to the magnesium chloride, okay? So you want to end up with the anhydrous. So you heat this up, you heat it for a while, and then what they're going to tell you is that after the first heating you have a mass of 23.982 grams. Then you heat it a second time and it's 23.976. Notice that the mass has gone down a little bit, okay? Then you hit it the third time and now the mass is remaining constant. So in a lab procedure with hydrates, that's typically what you want to do. Just heat it the first time, then typically you kind of crush it up a little bit, okay? It's like take a stirring rod and crush it up a little bit. And then you heat it a second time and then you compare those masses to make sure that you've heated it up enough. Because if you keep losing mass, then, oh, all right, we haven't got rid of all the water. So here's what you have to understand is that any loss of mass in there, you're not losing magnesium chloride, you're losing water. So what you're trying to figure out, and this is a bigger truth, is that this is either, let's say it's 4, okay, whatever it works out to be. So that means that either you have 4 molecules of water for every 1 magnesium chloride. It also is a ratio of moles, which means that you would have 4 moles of water to 1 mole of magnesium chloride. Okay, so, but it is not a ratio of mass. So if this is 4, that doesn't mean that you have 4 grams of water to every 1 gram of magnesium chloride. So this is either a ratio of moles or it's a ratio of particles, but it is not a ratio of mass. Okay, so keep that in mind as you work through the problem. Now I'm going to shut up and turn you all loose. Okay, so if that first part it says, well, explain what's in can correctly conclude that a hydrate has been heated a sufficient number of times, all you have to just say is like the mass isn't changing after that 3rd or 4th heating. That's all you have to say. And then on B, calculate the number of moles of water lost in the compound is heated and determine the formula of the hydrated compound. So here's your step-by-step process that you have to do with hydrates. Okay? So you keep in mind your end game is you're going to take the moles of water and you're going to have to divide that into the moles of your magnesium chloride. Okay, so you have to find the number of moles of both. Okay, that's the whole key to this. So the whole key is also figuring out, okay, you got a whole bunch of data, which data do you start with? Well, the first thing you want to figure out is how many grams of water. So this was that mass that you started with. This is the mass after it was heated. So anything that you lost is going to be your grams of water. Okay? So this is how much water that was lost because that was the difference between the two. Now, to get the grams of magnesium chloride that was still in there, okay, a couple of things you can do. There's actually 2 ways you can do this. One is you start with that mass. You subtract out the mass when it was empty. That tells you the total mass of the magnesium chloride and the water that was in the crucible. You subtract out the mass of the water, boom, there's the mass of magnesium chloride that was in there to begin with. Okay? So, now, once you get those, then you've got to find the moles of each one. So, Mr. Carter, how am I going to find the moles of water?
Divided by the mole and moles.
Which is?
I got 18.02.
Yep, so you can just call it 18. And what'd you get from the number of moles?
Like 0.102.
Well, 0.102,
103.
0.103 moles of water. Now you're going to do the same thing with the magnesium chloride and divide that by the molar mass. You're going to get 0.0171 moles of magnesium chloride. Now, here's the kicker. What's bigger, the moles of water or the moles of magnesium chloride? Moles of water. So that way, when I find that formula, I know the coefficient that goes in front of the water is bigger than what's going to go in the magnesium chloride, because I have more moles of water. If this was bigger, okay, then I'd have like maybe 5, whatever it is, of magnesium chloride to 1 of water. And that doesn't happen with hydrates, okay? When you have hydrates, it's always 1 of the formula units to a certain number of water molecules, okay? You never have more of the ionic compound than you do of the water. If you do that and that's what you get, I'm guessing that you screwed something up. So anyway, so if you take that moles of water, 0.103, and then you divide that by the 0.0171 moles of your MgCl2, you get 6, so it's MgCl2 got 6H2O. Good with that? Okay. Now, then, and they like asking these questions. It's like what-if questions. So on C, a different student heats a hydrated in an uncovered crucible, some of the solid spatters out. Spatting will have what effect on the calculated mass of the water lost by the hydrate? So, if you heat this up, and some of it flies out, okay, well, what do you think is that, what's that going to do to the mass of water that you think you lost? You think are you going to end up thinking you lost more water than what you should have, or less water than what you should have? More, okay, because it's going to look like you lost more of that water, okay, because some of that's going to splatter out, which is why you put a cover over the top of it. Okay. Now, so when you get to part D, now this is the situation for those of you that are taking the test. Let's say you get on that first part and you have no idea how to do hydrates. It's like, oh, man, I have completely spaced this off, okay? If you look at what's happening on D and E, it really doesn't have anything to do with the hydrated portion of what's happening up on the first part. So, if you get to the first part of a question and you go, I am so screwed, don't panic, okay? Because a lot of times they're going to start you over with something different. So, you got anhydrous magnesium chloride and potassium nitrate, determine the percent by mass, okay, uses excess over nitrate, just the chloride is AgCl, right? So, you want to determine the mass of the AgCl, okay? So in this beaker, right, you've got magnesium chloride, which is going to exist as magnesium ions and chloride ions, okay, and potassium ions and nitrate ions, right? Now, if that's all you mix together, okay, neither one of those is going to form a precipitate. Potassium chloride is soluble because it's group 1. Magnesium nitrate, even if you do a double displacement reaction, is still going to be soluble, okay? So that's not going to get you a precipitate, okay? It's not going to. But what you can do then is that you can add silver nitrate. So the silver nitrate ions are going to come in here and go, hello, chloride ions, okay? And they're going to form such a tight bond that they're going to form a precipitate, okay? This would be like a white chunky precipitate at the bottom of the beaker. So basically, you've got to get rid of that. You've got to get that precipitate out of there. So what are you going to do? Ben?
Use some filter paper to separate the precipitate
Yeah.
from the solution.
You can say, I'm going to take a funnel, I'm going to put in filter paper, I'm going to pour it through. Okay? So that's going to get you out the precipitate. But then what else do you have to do?
Wait,
Huh?
you have to weigh it?
You got to do something in between.
Heat it up
Why?
to get the stuff off of it. It's wet.
Yeah, you want to dry it. Okay, so you can either let it sit overnight, unfold it and let it sit overnight, or you can heat it. Somehow or another, you have to let it dry, so that the only thing you want on there is the silver chloride, because this is going to be very much in an aqueous solution, right? So you're going to heat it up, you're going to let it dry, and you technically also you should wash it. Okay, take some deionized water so that way you're getting rid of the ions that might be attached to it, the only thing you have. So technically you should say you should wash it, dry it, and then you're going to find the mass of it that way. So then, student determines the mass to be 5.48 on the basis of the information. Calculate each of the following the number of moles of magnesium chloride in the original mixture. So this is going to boil down to a stoich. So if you look at the initial double displacement reaction, right, you're going to get magnesium nitrate and potassium chloride, okay? But neither one of those are insoluble, okay? So then what's going to happen is that your KCl, here's the actual reaction that's going to happen, is that KCl is going to react with the silver nitrate, and you're going to get silver chloride and potassium nitrate again. Okay, so basically you're going to end up making more potassium nitrate out of this deal. So, but here's the point though. Notice on this one, everything is in a 1-to-1 ratio. So if you look at this, you've got, what do you get? 5.48 grams of silver chloride. So what's the first thing you're going to have to do with those grams of silver chloride?
Moles.
Convert it into moles. So the molar mass of that is 143.32 grams of AgCl. 1 mole of AgCl. Okay? So then, from there, you can go, oh, okay, hey, for every 1 mole of AgCl, I get 1 mole of chloride ions. Okay? Because that everything's in a 1-to-1 ratio. Okay, so that gives me 1 mole of chloride ions. And then here's the kicker though. So if you go back to this initial balanced equation, to balance this out, you've got to have a 2 here, because you've got 2 chloride ions over here, and then you've got a 2 here. So now with those chloride ions, because they want you to work backwards and figure out the moles of magnesium chloride, right? And then you work backwards to go, okay, I want that moles of magnesium chloride. So there's 2 moles of Cl minus to every 1 mole of magnesium chloride. So you're going to start with your moles of silver chloride, or grams, roll that into moles of silver chloride. 1 mole of silver chloride gets you 1 mole of chloride ions from this reaction. And then, then if you come up here, because now this is going to determine your moles of magnesium chloride, so then you got to put, if there's 2 moles of chloride ions, every 1 mole of MgCl2. Okay, so it's like you got to do the net ionic, and then you got to work your way back to that original double displacement reaction. Okay, so you kind of got to do like this double conversion. So anyway, so if you do that, you get, if you do all this math, you get 0.0191 moles of magnesium chloride. Okay. And then on part 2, then it wants the mass of magnesium chloride. Okay, well that's simple. That's the easiest step of all. Moles of magnesium chloride. And 1 mole of magnesium chloride is 95.3 grams. And you get 1.82 grams of MgCl2. So that had to be the grams of magnesium chloride that you had to start with. Now, the ultimate question here says the percent by mass of magnesium chloride in the original mixture. So the original mixture started with 2.94 grams. So you're just going to take that 1.82 grams of magnesium chloride and divide that by that total mass of, what's total mass? 2.94 grams. And you get about 62%. So this is actually a cool way to do something like this. It's like, oh, okay, you've got a mixture and you have to find some way to filter it out. Well, here's the problem. Just physically, if you look at that first reaction of magnesium chloride and potassium nitrate, if you put that in a solution, yeah, you're going to get a double displacement reaction, but you're not going to get anything that you can filter. You can't filter either one of these out because of the fact that they're still going to be soluble. So then you go, okay, well, let's figure this out. Let's add some silver nitrate, because you know the only thing that silver nitrate will precipitate out is that chloride ion. Then once you get that chloride ion, and that mass of that silver chloride, then you can work backwards and figure out that mass of that MgCl2. So it's actually a clever way to say, okay, well, I can't physically separate it, but I can bond it with something, get that separated out, and then work backwards to that mass of that magnesium chloride. So it's kind of a cool way to do it. Okay, so got that one. So now let's talk a little, this should be somewhat relevant. So try that one on the back side, where it's got the 2009 question number 5. You got delta H, delta S, and delta G. Okay. So last week, I couldn't have given you this question because you all didn't know anything about delta S and everything else, but now we can. All right, so let's look at, this is a classic situation. If I were you all taking this test, step back and look at this overall picture about what's happening, okay? So first off, look at your delta G's on X and Y, okay? The ones that you have that information for. What do you notice about your delta G's? Positive. Are those reactions even going to happen at 298, right? They're not spontaneous, okay? So neither one of those first two reactions are spontaneous. Now, look at your delta H's. Are both of those reactions, in terms of enthalpy, is that favorable with enthalpy? Why not, Mr. Carter? You shake your head no.
Because it's endothermic and Mother Nature likes a hot mess.
Beautiful. That's such a wonderful answer. Okay? So this is cold, right? It's endothermic. You got to pump energy into this. So that means you're going to be breaking bonds. Okay? Now, but what about your entropy terms? Are those favorable thermodynamically? Your entropies are, because they're positive. So right now we got a cold mess going on. So here's the deal. You got a cold mess going on. So at least you have the potential to make these reactions become spontaneous. You could, right? But would that be above a certain temperature or below a certain temperature? That's going to be, you're going to have to go above a certain temperature. So at 298 Kelvin, or Celsius, 298 Kelvin, you're too low. So basically what's happening conceptually is that if you look at delta E, delta G equals delta H minus T delta S, right now, this entropy term is too small, So when you subtract it from that delta H, you're getting a positive delta G. So to make these two reactions become spontaneous, you want to run it at a higher temperature than what it's at, or at a lower temperature? Party girl.
Higher?
Yeah, because you want to make this term get big enough so that when you subtract it from delta G or delta H, you get a negative delta G and it becomes spontaneous. Okay? That's what you're looking at. All right. So, on that one where you write that Kp expression, okay, Kp, what is that P going to stand for? Pressure, concentration, what? Pressure, right? So the only thing that you're going to worry about are the things that can be a gas. So that Kp, now, is it reactants over products or products over reactants? Products over reactants. So you're going to have the pressure of your CO times the pressure of your H2, and what's the other one? And then divided by the pressure of your water. Okay? That's all you have to do. Now, don't worry about the carbon because that's a solid. Okay? So don't put that in there. It's only the things that can be pressures. Okay, so we got that one done. Now, then you've got the next question. Well, the equilibrium constant increase, decrease, remain the same if the temperature rises above 298. Justify your answer. Okay, so here's the whole kicker to this. So it's asking, which one is it asking about? Question X. Okay, so this is an endothermic reaction, right? Okay, because you have a positive delta H. So here's the deal. You got to take energy into the system. It's endothermic, right? Okay, so what that means is that energy is showing up as a reactant, okay? If it's exothermic, energy shows up as a product. So that's something to remember. If it's an endothermic reaction, heat is a reactant. If it's an exothermic reaction, heat is a product, okay? So if you dump more and more energy into this, if you raise the temperature, then if you look at what's going to happen, what is it asking for, Kp? Okay? So, because if you put more and more energy into it, it's going to force it more to make more product, okay? So what's going to happen then is that since it's endothermic, you're going to force that over to that product side, and it asks for Kp is going to increase because of the fact that mathematically you're making higher pressures of that carbon monoxide and hydrogen, and because it's an endothermic reaction. Okay? Got that. Now, on part C, then it says, for reaction Y is the value Kp greater than, less than, or equal to 1, justify your answer. Okay? So here's the deal. Look at your delta G, okay, and this is where this whole thing kind of becomes a big idea. You have a positive delta G, so is the reaction spontaneous in the forward direction? No, okay? It's not favored. So think back to when you had, you've all dealt with K values, Ka, right, Ksp. Are those really big numbers or are those small numbers?
Small.
They're small numbers because they are not favored in the forward direction. Okay? Okay? Not. That's what makes the K values really small. So that's one of the overarching themes. And so if you look at what's going to happen here, so because of the fact that you're going to have a non-favored reaction, it's not spontaneous, what do you think that K is going to be less than? Is that K is going to be this? So that K is going to be less than 1. Because if it was greater than 1, it would be a spontaneous reaction. Delta G would be a negative value. Okay? All right. Now, so then on D, for reaction Y, which is larger, the total bond energy of the reactants of the total bond energy of the products. Okay? So here's the deal. So in reaction on D, it's asking about, what's it asking for? About Y. Okay? So you have an endothermic reaction. Okay? So it's endothermic. So if you look at what's happening on this actual reaction, you've got to break bonds first. Okay, so you've got to put energy into the reactant side to break the bonds. And then you're going to release energy once you form new bonds. Okay? So if you look at what's happening, that's actually CO2. So you're going to put energy in to break the bonds, and then energy is going to be released on the other side once you form new bonds. So since it's endothermic, you put more energy into breaking bonds than you get out in forming new bonds, or do you get more energy in forming bonds than you do inputting energy into break bonds? Which one, Mr. Carter?
Takes more to break bonds.
Yes, so I'm going to put more energy into breaking bonds than I am in that's going to get released on the formation of bonds on the other side. Okay? So I got to put more energy in to break them than what I'm going to get out on the other side. So this is what we talked about today. Is the following statement true or false? On the basis of the data, can you predict that reaction Y will occur more rapidly than reaction X will occur? Okay? So what they're looking at there, I don't even know what they're really looking at. Okay? Because here's the bigger truth. First off, neither reaction is going to take place because they're both non-spontaneous. Okay? So you can make that argument. It's a stupid question because neither reaction is going to take place. But here's what they're getting at, is that the statement is false because just because a reaction is spontaneous or non-spontaneous does not indicate anything about the speed of the reaction. So that's what they were getting for on that question, is that they just want you to realize that thermodynamically it doesn't have anything to do with rate, it just tells you if the reaction is going to take place. Okay, so consider reaction Z at 298 Kelvin. So here's the deal. So you got 2CO as a gas turning into C plus solid plus CO2 gas. So, party girl, what's going to be the sign of delta S? Is it going to be positive or negative?
Negative.
Why?
I said because you have to flip both of the top ones to get the bottom one, so I think I just got lucky because I don't know.
That is part of it, okay? But here's the deal. Just look at this, okay? How many moles of gaseous reactant do you have?
2.
2. How many moles of gaseous product do you have?
1.
1. So you're going from 2 down to 1. So since you're decreasing the moles of gaseous materials, delta S is going to be a negative number. Okay? You eventually need to do what you did. It's a god-awful amount of work, but yeah. So, then on part F it says determine the value of delta H for the reaction. So this is what you did. Okay, you just did it for delta S. They ask you for delta H. Now, here's basically what are they asking you to use? Which law are they asking you to do on part 2? Anybody remember? It starts with letter H.
Hess's law.
Yeah, you're trying to do Hess's law. Okay? So you've got to arrange those top 2 equations so that when you add them together, you end up with that third reaction. Okay? That's what it's like, do you understand Hess's law? And it's weird because they don't actually come out and say, hey, use Hess's law, flip the top 2 equations so you can get the third one. So they're tricky that way because they're going to say, hey, can you figure this out? So anyway, so if you do, you got to switch both of them, then you can get the waters to cancel out. No, you flip the bottom one. You flip the bottom one, that was it. And so then you can get this reaction, and your delta H then becomes negative 172 kilojoules per mole. Okay? Actually, you do have to flip both of those, don't you? Yeah, you got to flip both of them. Okay. Then, on part 3, sealed glass container contains carbon monoxide, a small amount of carbon. As the reaction occurs, as the temperature is held constant, will the pressure in the reaction vessel increase, decrease, or remain the same? So, what'd you get on that one, Ben?
I didn't get to that one.
Okay, well here's what's, look at this. It goes back to this idea. You're going to start with 2 moles of gaseous reactant, right? You're going to only end up with 1 mole of gaseous product. So what's going to happen to the number of moles of gas in that container?
Decreases.
It's going to decrease. So what's going to happen to the pressure?
Decreases.
It's going to go down. Okay? So your pressure is going to drop because you're starting with 2 and you're only ending up with 1. Okay? All right. Now the last one goes pretty fast. Okay? So even though there's 2 separate problems, like this first 6, it only has part A and B. Okay? And then the other one just has A and B as well. So try both of those. Okay, so let's hammer through these last ones pretty quick. So this goes back old school KSP, right? So when's the only time you use K across the board? What's the only time you use K? What's that one unique condition? And it's at equilibrium, right? So they were nice and they gave you the reaction, right? So this is going to ionize into magnesium and 2 hydroxide because that's all there is. It's like there's nothing else in it, okay? There's no hydroxide to start with. You just say, okay, here's what we've got. So now here's what you have to be careful of. Because and you're going to get 2 hydroxide ions for every 1 magnesium, right? So when you write out that Rice chart, you're going to have X and you're going to have 2X. So this is going to be your magnesium ion concentration at equilibrium, which is X. But what's the concentration of your hydroxide ions? 2X. But what's going to happen to that 2X concentration? It's going to get squared because there's a coefficient 2 in front of it. Okay? So what you're going to end up with is your KSP is going to equal 4X cubed. Okay? Now, if it was just a 1-to-1 ionization, it would just be X, and it would just be X squared. So, if there was 3 of them, it would be 3X, and then that would get cubed. So, your KSP is going to equal 4X cubed, so you have to divide by 4, and then take the cube root. Okay? So, buddy, do that. Take that KSP, 1.8 times 10 to the negative 11th, times 4, and then take the cube root of that.
Times 4 divided by 4.
Excuse me, divide by 4, then take the cube root of it.
1.43 e to the negative 4th.
You sure?
Yeah. 1 point, oh,
Got me at 0.65.
What'd you get?
Wait, no. Just divided by 4?
Yeah, you're gonna multiply by 4 and then take the cube root of it.
1.65 times 10 to the negative 4.
yeah.
That's what I got.
Yeah.
Moles, right? And that, now, that's the molarity. So that's moles per 1 liter, right? So the kicker to this is that how much are you going to dissolve in just 100 milliliters of it? So they were nice, and they said, oh, here's the molar mass. 1 mole, 58.32 grams, right? But then, that last step, you're going to multiply by 0.1 liters, and you get 9.6 times 10 to the negative 4th grams. And that's a really, really, really small amount, okay? Because like even our big dog scales, which go up to 4 decimal places, so imagine that, y'all work with that enough, trying to measure out, basically it'd be 0.000 and then 9. It's like, okay, let's take a pair of tweezers and drop a few granules on it. Okay, now, those of you all have been through AP Physics 2. So we haven't talked about lattice energy, but here's lattice energy is basically how much energy it takes to pull something apart, break up that ion. So if you look at this, the whole key to this is that you have magnesium. Now, on the periodic table, where's strontium relative to magnesium? Below it. So which one is going to have a bigger atomic radius, the magnesium or the strontium? That's going to have a bigger radius, right? Okay, so this is going to have a smaller radius. So if you look at what happens, so here's this nucleus, right? Here's the nucleus of strontium. So magnesium has electrons here, but strontium is going to have a bigger electron cloud, okay? So if you look at Coulomb's law, where you have F equals K, Q1, Q2 over distance squared, okay? So how you can explain that difference in lattice energy is that because the magnesium has a smaller radius, therefore, because of that shorter distance between the charged particles, that's going to require more force to break that bond. Okay? So you would have to invoke like Coulomb's law and say because they're oppositely charged particles, the magnesium is closer, therefore there's more of an there's a stronger force that has to be overcome. That's why that lattice energy is bigger. Okay, so let's move on to the question number 6 on that back side. And it's odd. This is what, if you look at how like the AP questions have changed. So they used to be like this 2009. There was one big massive question, like parts A, B, C, D, and E. So these questions are off of 2017. Okay, so they've gone to like shorter but more questions, right? So it's just like boom. Here's this high impact kind of question where they don't necessarily go through all of these big complex calculations like they had you do before. All right, so here's the deal. So you want to figure out the hydrogen peroxide, right? Titrants, which is a fancy name for, hey, what are you going to put in the graduated cylinder and open up? So here's the deal. You want to calculate the E0 value for these. So if you look at what this chart is, okay, is this chart a reduction table or an oxidation table?
Reduction.
How do you know?
They're giving me electrons.
Yeah, they're all gaining electrons, right? So this is a standard half reaction table, right? They've only given you a portion of it. So if you look at this, so you want that reaction between the dichromate and the hydrogen peroxide. So which one are you going, on this one you have to figure out, you got dichromate plus hydrogen peroxide yielding Cr3 plus H2O, right? So here's the deal. So one of these is going to get flipped, okay? That's the only way this thing is going to happen. So you want the reaction between dichromate and H2O2 at 298 degrees. So obviously you've got to have that dichromate one, which is going to be 1.33, okay, volts. Then, if you look at this, if you look at what's going to happen here with that H2O2 to end up with O2, so here's the deal. You can't, here's what you have to be careful. First off, this has to be a redox reaction. It can't be a reaction. So one of these has to get flipped. So in terms of which one you're going to flip, you have to flip one that has hydrogen peroxide as a product, as a reduction, so you can flip it, and then otherwise you can't. Here's what you're tempted to do is take the that H2O2 and the CrO2 and just use those. It won't work because then you have a reaction and you have to have a redox reaction. So you've got to flip the bottom one so you can have hydrogen peroxide as a reactant, and then that's what's going to get flipped. Did I start that camera back up? Okay, thank God. Honestly, if I did all of this and I wasn't recording this. Oh, okay. Anyway, so you got 1.33, you're going to flip the bottom one, you get negative 0.70, and you get 0.63 volts. Now, big picture. you have a positive E naught value. Out of this, you have a positive E naught value. So is this reaction going to be spontaneous? Yes. Okay, so this will work. Okay. Now, then, if you look at the reaction between CO2 plus and H2O2, right? So with this one, you've got to start with the CO. So the only one that has CO2 as in there is one that you're going to have to flip. So you're going to have negative 1.84, which is going to be that top reaction. So that one's going to get flipped. And then you're going to keep that dichromate one, which is 1.77, and you add that together, and you get a negative 0.07 volts. So what that means is that would that reaction happen? No, because you have a negative E naught. So what that means is if you mix cobalt ions with hydrogen peroxide in an acidic environment, nothing's going to happen. It's just going to sit there. But if you put dichromates in hydrogen peroxide in an acidic environment, the reaction is going to take place. Okay, so that's the difference between the two of them. So then that leads us to the next question. Based upon the calculated values of E naught, student must choose which one. You want to choose the one with the dichromate because of the fact that that's the one that will produce a negative or a positive E naught value. And then it wants to calculate delta G. So you got to go delta G naught equals that Faraday's constant, F E naught. You get negative 6 times 96,500 times 0.63 volts, and you get negative 360 kilojoules per mole. You got a negative G naught. Guess what the reaction is?
Spontaneous.
Spontaneous. All right, kids, let's call it a night.